All right, let's dive into something that, believe it or not, connects, well, pretty much everything. From how you're seeing me right now to the fundamental nature of reality itself. And it all kicks off with a little puzzle. Okay, so take a look at this. At first glance, it just looks like a mess, right? A bunch of random red and green dots. But it's actually not random at all. If you were wearing 3D glasses, a hidden image would literally pop right out at you. And the crazy part is, your brain does this exact same trick all day, every day. It's constantly taking in light, hunting for patterns, and finding the relationships between all those little points of data to build the world you're seeing. So, how on earth does it do that? And that question leads us to two what seem like totally separate mysteries. First, the one that's literally happening in your head as we speak. How does your brain take two flat 2D images, one from each eye, and magically build this rich 3D world around you? And then, let's jump to the other end of the spectrum, to a puzzle from the very heart of physics. How can one tiny little quantum particle be in a bunch of places at once, exploring all possible paths at the same time? Now, what if I told you the answer to both of those questions is exactly the same? That there's one single, powerful idea that unlocks the magic of your own vision and the deepest secrets of quantum mechanics. That big idea is correlation. And no, I'm not just talking about something you learned in a stats class. In physics, it's so much more. You can think of it as the universe's glue. It's the principle that defines relationships and ultimately builds complexity. So, at its core, correlation is a physical measure of how things are connected. We're not just talking about numbers on a spreadsheet here. We're talking about the relationship between the images from your two eyes, or between atoms bouncing around in a gas, or even between a single quantum particle and, well, the rest of the universe. Okay, so to really get a handle on this cosmic glue, scientists have a pretty awesome toolkit. The best way to think about it is like having two different lenses you can use to look at the world. Each one shows you a different kind of connection. So on one side, you've got what are called second moment measures. These are awesome for spotting simple, basic trends. Stuff like, if this thing goes up, does that thing go up too? But then, on the other side, you've got multi-moment measures. And these are way deeper. They don't just spot trends. They measure the total useful information, or what you could call the surprise factor in a relationship. Let's start with that first lens. A big tool here is something called cross-covariance. I know it sounds complicated, but the idea is actually super simple. It's all about comparing two things to see how well they match up. Imagine you have two pictures, and you're just sliding one over the other until, bam, they line up perfectly. That's the basic idea. And what's really cool is that we can boil this whole relationship down to one simple number, the Pearson correlation coefficient. It's just a scale from -1 to +1. +1 means they're perfectly in sync. -1 means they're perfect opposites. And 0, that just means there's no simple linear connection. It's just a really elegant way to summarize a relationship. And check this out. This shows you just how big of a deal correlation is for, being sure about something. See those top dashed lines? That's where the correlation is really high. And notice what's happening. You need a ton of data points. You have to go way, way out to the right just to get your uncertainty down. It's a perfect illustration of a key idea. When your data is super correlated, each new data point isn't very surprising. It doesn't tell you much new stuff, so you need a whole lot more of it to feel confident. Okay, but what if the relationship is more complicated than just a simple trend? What if we want to capture the whole story? Well, for that, we need to switch to our second, more powerful lens. Multi-moment measures ask a deeper question. Not just do these things move together, but how much useful information is actually shared between them. And the star of the show here is something called KL divergence. The absolute best way to think about this is as a measure of surprise. For real, imagine you think a coin is fair, 50-50, but then you flip it, and it comes up heads, and heads again, and again. With each flip, your surprise grows, right? KL divergence is the math that puts a number on that feeling of surprise. It measures the gap between what you thought would happen and what really happened. It's a direct measure of new information. Okay, I know what you're thinking when you see this formula. Don't worry, don't let the math scare you. You do not need to memorize this. The big takeaway here is super simple. Unlike that nice, clean -1 to +1 score, this thing captures the entire relationship. It gets the whole shebang, the full, rich, messy, complex connection between two systems, not just a simple little trend. All right, so we've got our toolkit,
we've got our two lenses for peering into the universe's hidden connections. Now comes the really fun part. Let's actually use them and go solve those mysteries we started with.
So, back to that first question, how do you see in 3D? It turns out your brain is an absolute master of cross-covariance. It's constantly taking the two slightly different pictures from your left and right eyes, and like a supercomputer, it's calculating the tiny shifts, the offsets, for every single point. And that pattern of shifts, that's what your brain translates into depth. It's literally correlation in action, happening inside your head this very second. And it's not just our brains doing this. We've built technology that uses the exact same principle. It's how your phone unlocks when it sees your face. It's how software can build a stunning 3D model of a building from just a few flat photos. It's even the secret behind JPEGs. They work by finding parts of an image that are really similar, highly correlated, and then they just simplify them to save space. But the applications go way beyond just pictures and gadgets. I mean, correlation analysis is one of the most fundamental tools we have for just understanding the world around us. For example, geologists were actually some of the pioneers of these methods, using them to understand the complicated, grainy patterns in rocks. Ecologists use correlation to check their models against real-world data, to see if their predictions actually hold up. And geneticists? They use it to track how mitochondrial DNA is passed down, literally following the correlation of our genetic code through time. And this is where things get really, really wild. Remember our surprise number, the KL divergence? Well, in physics, it has another name, thermodynamic availability, which means the amount of useful work you can get out of something, like the energy in this container of gas, is directly tied to its KL divergence from everything around it. Think about that. Information and energy are basically two sides of the same coin. Wild. So we've seen how correlation builds how we see, how we build technology, even how we understand energy. But its deepest, most mind-blowing role is at the very bottom of it all, in the weird, wonderful world of quantum mechanics. Pretty much the entire secret of quantum mechanics, particles being in two places at once, quantum entanglement, all that weird stuff, it can be boiled down to this one incredible line. State uncertainties, unconstrained by relationships to the outside world, result in the simultaneous exploration of all possible paths. So what does that mean? It means this. When a quantum particle is all by itself, when it has zero correlation with the outside world, it's completely free. It exists as just a haze of pure potential, exploring every single possible path it could take, all at the same time. It's only when that particle interacts with something, when it becomes correlated with the outside world, that it's forced to pick one and snap into a single definite state. All that quantum weirdness we talk about, it's really just what happens when there's a lack of connection. Wow. Okay, so we've gone all the way from a simple optical illusion to the fundamental fabric of reality itself. So, what's the big picture here? What's the main takeaway from all this? It means that correlation is so much more than just a statistic. It's the physical measure of information itself. It's the engine that drives our perception and the blueprint for our technology. It's literally the dividing line between the weird quantum world and our everyday classical world. And maybe, just maybe, the most important thing is this. Correlation is how the universe creates complexity. From stars to planets to us, everything complex that exists is a result of new connections, new correlations being formed. When you think about it, the entire story of the universe is the story of new and more complex relationships being built, which leaves us with a really fascinating thought. As humans, as tool builders and storytellers and networkers, we are one of the most powerful forces for creating correlation the universe has ever produced. So the final question is, for you, what new connections are we building today?